Hi, welcome to Viveka physics classes, and today we're gonna solve a problem based on the concept of motion of the charged particle under the electric field produced by a dipole. And also we can study the angular oscillations performed by the charged particle under the dipole field. Take a look on the problem. Okay, in this problem we have a small electrically charged bead of charge q and mass m. Initially, the bead is placed at point A on the frictionless insulating circular ring. Mean to say, the ring does not offer any friction for the motion of the bead on it. At the same time, as the ring is made up of insulating material, there is no electric contact between the ring and charge bead. Okay. Now, at the same time, a small electric dipole of dipole moment P is placed at the center of the circular ring such that its dipole axis lies on the plane of the circular ring. Now, initially the bead is placed on the perpendicular bisect of the dipole, mean to say at point A. Now, on the basis of this, we need to answer for these 4 questions. The first one, write the speed of the bead when it reaches the position theta as shown in the figure. Mean to say, when the bead reaches the point B, the position vector of the bead makes an angle theta with the dipole axis. At this position, what is the speed of the bead? They are asking. That is the first question. Now, in the second question they are asking, what is the normal force acting on the bead by the ring? Okay. In the third question, they are asking, how does the bead move after when it is released? And where will the bead first stop after being released? Mean to say, when the bead is released at point A, what is the nature of motion of the bead? Mean to say, whether it covers the circular path or semicircular path, what kind of path? What is the nature of the motion of the bead? And also we need to answer, after when the bead is released at point A, where the bead is going to stop for the first time, okay, on the circular ring. Now in the fourth question they are asking that, how would the bead move in the absence of the ring? Mean to say, if the ring is not there, if the ring is absent, then what is the nature of motion of the bead in the absence of the ring? That is asked in the fourth question. Now, one important note is given. While solving these questions, we need to ignore the gravity. Mean to say, we should not consider the effects of gravity while answering these 4 questions. Okay. First, let us study what happens when the charge bead is released at point A under the electric field of the dipole. Here, one thing that we need to understand, that when the charge bead is released at point A, it will go under a semicircular path around the center of the dipole O. Now, when the charge bead reaches the point D, momentarily it will come to rest at point D so that its velocity becomes 0 at point D. But the bead will not be permanently at rest at point D. It's because as soon as it reaches the point D, immediately it will start to slide down so as to reach the point A again by covering the same semicircular path around the center of the dipole O. Now, what happens when the bead reaches the point A? Even after reaching the point A, the bead will be momentarily at rest so that its velocity is 0 at point A. But immediately the bead will start to slide down so as to reach the point D again by covering the same semicircular path around the center of the dipole O. Now, this repeated semicircular motions of the bead around the center of the dipole will continue for a long time. In other words, we can say that when the bead is released at point A under the electric field of the dipole, the bead executes angular oscillations around the center of the dipole O. Okay. Now, question arises, why the bead executes angular oscillations around the dipole? To understand this, let us draw the electric field lines around the dipole so that we can study the motion of the charge bead around the dipole. Here, in the second diagram, we can see that we have drawn the electric field lines around this dipole. Okay. Now, as the dipole is shifted from here to here, the points A, B, C and D are also shifted from here to here accordingly. Here you can see point A, B, C and D. Now, let us resolve the electric field produced by the dipole at point A, B, C and D. At point A, we have a tangential component of the electric field of the dipole, but the radial component of the electric field is 0 at point A. Similarly, at point D also we have tangential component of the electric field, but the radial component of the electric field is 0. It's because the point A and D lie on the perpendicular bisector of the dipole. So, for any point lying on the perpendicular bisector of the dipole, the radial component of the electric field will be 0 and tangential component of the electric field will be present. Now, even for this point and this point and this point and this point, the radial component of the electric field is 0 because all these points lie on the perpendicular bisector of the dipole. Now, when the bead is released at point A with an initial velocity 0, the bead experiences a tangential force under the effect of tangential electric field, which is given by the product of magnitude of charge of the bead into tangential component of the electric field. Now, under the action of this force, the bead will start to slide down. Okay. Now, let us consider any intermediate point B on the semicircular path of the bead such that E is the electric field of the dipole at point B, which is taken along the tangent drawn on the electric field lines reaching the negative charge. Now, this electric field can be resolved into two components. The first one, the radial component of the electric field, which always acts towards the center of the dipole O, and other one, tangential component of the electric field at point B, which always acts along the tangent drawn at point B on the semicircular path of the bead. Now, when the bead reaches the point B, it will experience a force under the action of radial component of the electric field, which is given by product of magnitude of the charge of the bead into radial component of the electric field, and this force is called radial force, and this radial force also acts towards the center of the dipole. Here in the diagram you can see both the radial component of the electric field and the radial force acting on the bead, both are acting towards the center of the semicircular path or towards the center of the dipole O. Now at the same time, at point B, the bead experiences a tangential force due to tangential component of the electric field. Now this force acts along the tangent at any point on the semicircular path. Now, if the bead is here, on the semicircular path, it will experience a radial force towards the center in this direction. Now, if the bead is here on the circumference, it will experience a radial force towards the center in this direction. Similarly, if the bead is here at point C, then it will experience a radial force towards the center. And at point B, the radial force will be acting towards the center in this direction. If we imagine the bead is here, then the radial force acting on the bead will be in this direction. Okay. Now, from this, we can conclude that at each point on the semicircular path, the bead experiences a radial force which always acts towards the center of dipole or towards the center of semicircular path. Therefore, from this we can understand that the radial force acting on the bead provides the necessary centripetal force for the semicircular motion of the bead around the dipole. Now as the bead moves from the point A towards C, the tangential force decreases and velocity and kinetic energy of the bead increases, such that exactly by reaching at point C, the tangential force becomes 0 and velocity and kinetic energy of the bead becomes maximum. So the bead has its maximum kinetic energy and maximum velocity at point C, and tangential force Ft becomes equal to 0 here. Now, during the motion of the bead from C to D, the tangential force increases in opposite direction, but velocity and kinetic energy of the bead decreases, such that by reaching the point D, the velocity of the bead becomes 0, so its kinetic energy also becomes 0. So for that reason, the bead is found to be momentarily at rest at point D. The bead experiences a tangential force. Immediately after reaching the point D, the bead experiences a tangential force which makes the bead to slide down so as to reach the point A again by covering the same semicircular path. So from this it is clear that under the action of the tangential force and radial force together, the bead executes repeated semicircular motions around the center of the dipole. Now, let us find the answer for the second question. As we have seen, in the second question they are asking that what is the normal force acting on the bead by the ring? We can see in the diagram that for the semicircular motion of the bead, the entire centripetal force is provided by only radial force. So in this situation, the ring need not exert any force on the bead so as to make the bead to move, because the entire centripetal force is provided by the electric field of the dipole. So for that reason, in this situation, the ring will not exert any normal force on the bead. Now, in the third question they are asking that how does the bead move after when it was released at point A, and where the bead will come to rest for the first time after being released. So here already we have discussed, when the bead is released at point A, how does it will move? The bead executes angular oscillations around the center of the dipole. That is the nature of the motion of the bead around the dipole. Okay. Now at the same time, where the bead will come to rest for the first time after when it was released at point A. So the D is the point in the diagram where the bead will come to rest for the first time after when it was released at point A. So that is the answer for the third question. In the fourth question, they are asking that how does the bead move in the absence of the ring? Mean to say, if this ring is not present, how does this bead move? Already we got the answer here, because as the ring is not exerting any force on the bead, so the presence of the bead and absence of the bead doesn't matter here. Even in the absence of the ring, the bead will move in the same path. So the motion of the bead is not affected by the presence or absence of the ring. Now we have answered for the second question, third question and fourth question. We need to answer for the first question. In the first question, they are asking that what is the speed of the bead at point B when the position vector of the bead makes an angle theta. So at the position theta, what is the speed? Now to calculate the speed of the bead here, let us make use of the law of conservation of energy. Now let us apply the law of conservation of energy for the motion of the bead from the point A to B. That is, when the bead travels from A to B. At point A, so first let us apply at point B. At point B, we have the final kinetic energy Kf plus final potential energy Pf. That should be equals to, at point A, we have the initial kinetic energy Ki plus initial potential energy Pi. So, as I have said, as the bead is moving under the conservative field, the sum of kinetic energy plus potential energy always remains constant. That is, as V is the velocity at point B, the kinetic energy at point B is given by half mv square plus potential energy is given by the product of charge into potential of the bead at point B. That is equals to initial kinetic energy, let me take it as half m v naught square, where v naught is the initial velocity at point A, which is 0, later we can substitute, plus initial potential is given by charge of the bead into potential, electric potential at point A, half mv square plus, which is given by q into kp cos theta by r square, where p is the electric dipole moment and theta is the angle between the position vector and dipole axis, and r is the distance of the bead from the center of the dipole. Kp cos theta by r square, that is equals to half m v naught. What is the initial velocity of the bead at point A? 0. It is released with the initial velocity 0 at point A. So 0 square plus this. Okay, what is the electric potential at A? The same formula, Kp cos theta by r square. But here what is theta? If the bead is at point A, what is the angle made by the dipole with respect to position vector? It will be 90 degree. So therefore here I will use the value directly, cos 90. So it will be Kp cos of 90 degree upon r square. So at point A, the angle made by the position vector with the dipole axis is 90 degree. So here I am using cos 90. Okay, now you can simplify this one. Okay, what is that we are going to get? So this term is 0, this term is 0. So therefore we can write half mv square plus k qp cos theta upon r square equals to 0. Okay, now let us solve for V. Okay, now we can simplify this equation to find the speed of the bead. So therefore if you solve this equation, then what we are going to get? Here I'll write V square equals to minus 2kq, V square equals to minus 2kq p cos theta upon m r square. Now we got the expression for V square. Now let us solve for V. So therefore V equals to square root of minus 2kqp cos theta by mr square, where the condition is theta is greater than or equals to pi, where theta is greater than or equals to 90 degree or it is smaller than or equals to 180 degree. This condition is applied. See, here we have applied this condition because when the bead is released at point A, it will only execute semicircular motion, but it will not execute complete circular motion. Now I'll call it this equation as equation number 1. So equation number 1 provides the speed of the bead at point B. The radial component of the electric field at point B is given by ER equals to 2k p cos theta by r cube. The bead experiences the radial force which is given by the product of the charge of the bead into radial component of the electric field, that is Q into ER. Then what is the radial force acting on the charge? That is given by 2kq p cos theta by r cube. I'll call it as equation number 3. But we know that the centripetal force acting on the bead is given by mv square by r. So if I substitute the value of V from the equation number 1 here, so let us simplify this equation so that we will get expression for centripetal force. Here equation number 4 gives the centripetal force acting on the bead. Okay. And equation number 3 will give radial force acting on the bead. But as equation number 3 and 4 are identical, from this we can confirm that the centripetal force acting on the bead is entirely provided by the radial force acting on the bead, which is produced by the radial component of the electric field. Therefore, the radial force acting on the bead is equals to centripetal force acting, which is given by minus 2kq p cos theta by r cube, which is given by minus 2kq p cos theta by r cube. And here, okay, here negative sign indicates that the force acting on the bead due to the dipole is attractive.